All right, welcome back. We are GDD403. That's problem solving with data structures and algorithms in the winter 2023 semester at Canadore. And it says week 4 here, but it's actually week 6 of our broadcasts and recordings. And this is our 4th week together. But one thing that you're going to see is we continue to build on the stuff that we've done from our previous week. So it's kind of like it builds, and we're going slow. This is actually a slow version of me talking about stuff with you, and then building your capability until the second half of semester when we really do some crazy stuff. This is not the craziest or most difficult. This is just getting you guys warmed up with Unity, with C# and with all those things. Okay, so that's what we're doing. We're sitting at our calendar week 6, and the week of the February 17th is where we're at, right? So we're going to talk about some searching and searching algorithms. We did sorting algorithms last day, right? So that's we talked about the bubble sort and selection sort and insertion sort and merge sort, which is kind of an advanced sort, really quickly. And you know, so we're going to talk about some stuff this week to help you. Assignment 1 is officially due this Sunday, and assignment 2 is released, but we have to kind of get through the details. So last week we did more of that. We did more about the playing card simulation. We did some selection. We had a visual selection component that we added into our card simulation, where you can actually select cards by using your mouse to hover over them, as well as you know, kind of outline the cards with a simple outlining kind of plugin that we downloaded from the Unity Asset Store, with some mixed results. Weird, that little thing. And then your in-class exercise 3, you know, kind of was due last week. This week it's searching and sorting, searching algorithms and recursion. I want to talk about that a little bit, and more about your playing card simulation. We're going to see if we can add in as much as possible. All right, so that is what's due. Also, assignment 2, like I said, I've made it visible, but there's no details yet. But what I'm going to probably do, like I said, is build on assignment 1, so that it shouldn't be too crazy in terms of, like, you know, coming up with a brand new project structure or something like that is a lot. Typically, what I try and do, if we do those kind of things, is provide you with a starter. And a lot of times it's just easier. So we have a code base that's very similar that we're working with together. All right. So again, all of this is, you know, kind of the underlying motive with all of this is to try and get you guys to have better capability in Unity and in C# with data structures and algorithms. Other notes for next week. We have to talk about next week a little bit, because next week is, you know, there's always more stress around mid-semester tests and that kind of stuff. And your first test is happening next week. So what is this test? How is it going to work? No true, false, multiple choice in my courses. I've eliminated those kind of things. So there's no like actual test you have to answer. That doesn't make sense for me. It opens on Monday. So although your class happens on Friday, that's official, right? We're not going to use the Friday slot for a lecture. I'm not going to do that next week. Right, what we're going to do is I'm going to release the test as early as Monday. You'll have the entire week to kind of hack at it until I see you on Friday. On Friday, I'm going to answer any questions you might have. It won't be a long session. I'll go through the requirements, answer questions in terms of details, things that you need to do that I've asked you to do. So there'll be several tasks to accomplish. I'm going to measure the test or create the test based on that. You should be able to complete it within 2 to 3 hours. That's what I want to do. So again, it's not going to be something that I want you to do and it's going to take you like the whole week. That's not the exercise. That's like an assignment. So it's kind of like a mini assignment that you have all week to do. I know some of you have other tests next week as well. Like, you know, there might be some other courses that you have tests in, and that might take up some of your study time and prep time and everything else. And I understand that, but I want to give you flexibility in terms of when you start your test and when you finish your test. The test that we're going to do next week, which is like an active assignment or a practical test, will be due Friday at midnight. So that means that I open up on Monday, you have until Friday at midnight to complete it. That'll be all day. It's open book, open internet. You have all that stuff. You can use my code, your code, no one else's code for the test, but that you could search for the internet if you have questions on how you want to do something. And again, it will use Unity, and it will use, it may include lists, arrays, sorting, and searching of some kind. I may ask you to write a little algorithm on doing one of the things that we just talked about in the last few weeks. And it's just all around practicing the same kind of thing. So it might be very similar. You know, I may use the card pack that we've developed, you know, kind of over these weeks, because it's a natural progression. And, you know, it should be something that, you know, can challenge you a little bit, but it's nothing that's going to break you. That's the idea. That's my goal for the test. Okay, so it's not something like that. Okay, so that is the test, and that's going to happen next week. Again, the test is, I believe, worth 10% of your final grade, or 15. You can always test that. By the way, if you always want to know mark distribution and how that works, you can always go to course outline, schedule, and evaluations, and you can see the evaluation scheme here. And it tells you right here that, you know, the mid-semester test is worth 15% of your final grade. So it's worth, you know, more than your first assignment or second assignment. But it again, even though it's you know, it's 15%, it's not going to be as big as your first assignment or second assignment, because it's going to build on something that I want you to do. I may ask you in the test to also build something we haven't exactly talked about, maybe a variant of something that I've asked you to do. But again, you can search for all this stuff online, and then see if you can apply your knowledge that you've built up to whatever I'm asking you to do in the test. Okay, so that is the you know, the tests coming up starting on Monday, which is only a few days away, and then kind of spanning the entire week. Okay, questions around the test or assignment 1 before we move on? I know some of you are having, you know, heart palpitations around this stuff. They're like, hey, you know, I haven't done this kind of stuff before, or I'm not really great with Unity. It's not just one person, by the way. And you know, you're asking us to do this, and we're doing Unreal in another course, and our focus has been on that, and we just kind of scratched the surface on Unity, and now we're doing this. And I totally understand. That's why we're stepping to it slow. If you have questions, interrupt me, please. Let's get into what this topic is about for this week, and I'll try and make it as quick as possible as we move into the stuff that we're going to be doing in the in-class exercise today. Any questions before I move on? Sorry, I just saw that. Yeah, Justin?
Yeah, I posted something in the chat or a question.
I can't, not yet. I'll try. How about that? But I can't. I most likely is going to be Monday, like afternoon. I'm still working on it. Remember I talked about this earlier, that all the content that you're seeing is my content. There's nothing. I got zero content from anybody else. So I've got to put it together for you, you know, reasonably and all that stuff, and then look through it. And that's why it takes me a little longer to do everything in this course. So please forgive me. It's not because of anything else. It's because of that. Otherwise, in another reality where I've had all my content set up already, then yes, I think that's a great idea, because this way it gives you some time to, you know, start things on the weekend, and then, you know, that kind of stuff. I just don't have it right now. That's the reality. Okay, so I'm sorry. If it changes, I will keep this in mind, your request, and I'll see what I can do. Yeah. All right. So let's get into the stuff here that we're doing. So we talked about sorting last week, and sorting was kind of the first, you know, kind of fundamental algorithms that we're talking about. You can't do anything more advanced in the second half of semester without sorting. And having stuff that is sorted in a sorted order is really the way to go when it comes to, you know, doing any searching. Okay. And the reason for this, when it comes to searching, is if it's sorted, it makes our life a little easier. Why? Because that means I can start at the beginning especially for a sequential search, which we're going to talk about in a second. And then it's going to be more efficient. So again, there's always, if we want to make an efficient kind of search, especially if we're searching something that's a larger data set, then one step might be, I'm just putting it out there, we sort everything first. And if we sort everything first, that makes it so that we know that the numbers are in a minimum heap kind of example where the, kind of the value at the top, whatever you're searching for, the comparator that you're using is going to look at the top value. That's going to be, let's say, the lowest value or the highest, depending on if you're doing a descending or ascending sort. It depends on how you're going to do that. And then we can use that information to improve our searching performance. The worst case from a search performance is where things are completely in a random order with a large data set, and you're looking for items, in the data set itself. So we're going to talk about that. There are some advanced searching techniques we're going to use as well later on in the course. But for now, we're going to start with basic stuff, okay? And one thing is that whenever we're thinking about a search, we want to use some kind of list of objects or an array. Okay, that's how we start off. So let's think about these two searches, sequential search or a linear search. Kind of looks through a list. The assumption is that everything is in random order. That's the worst case scenario, right? And a binary search assumes that everything is in sorted order, okay? And there's going to be an advantage to using a binary search. Let's talk about a sequential search first. It's exactly what it sounds like, sequentially searching one item at a time. It's almost like if I want to find, I don't know, some kind of name in a contact list, and I start from the beginning and I go through the entire contact list until the end, right? With no knowledge of where the name is. Okay, that's what sequential searching is. It's like literally just going one at a time. And it's, and the way it works is you keep on searching the entire array, a linear array of elements. And when you think about that, if I'm looping through each element in the array, the best case scenario is that it's going to be the complexity or time-space complexity is going to be big O notation O of n, which means that I loop through the entire thing. And if there's n properties, 1,000 properties, it's going to take me 1,000 time parts, whatever you want to call it, right? If it's 10,000, it's going to take me 10,000, 10 times as long. If it's 100,000, it's going to take me 100 times as long, and so on. Okay, as we're going, right? And this is linear. That's why it's a linear search. It kind of, increments in a linear fashion. Where we get really bad is where we have, as an example, 100,000 or 200,000 or 1,000,000 items that we're searching through at the same time. That's where it gets a little hairy, and we have to find better ways of taking care of this. Now, sometimes we do several passes. We go through our data set once, we go through our data set again, and then we kind of organize things a little bit to make it better. But this is the worst case scenario where we do not assume that there's going to be any numbers in any order. Example, I'm looking for a number like 39, and I'm just going to look through the entire list until I find that number. And maybe return back, index of where that number is in the array. Bad, right? Really bad in terms of performance. Here's an example of a sequential search function that we might see. You can see here. Wow, I didn't even write the curly braces. And this is, by the way, in terms of coding style, this is terrible. I don't ever want to see you guys write for loops or if loops, if statements, or while loops or anything like that with a code block. You have a code block that's in curly braces. I never want to see you guys write code blocks somehow without curly braces, even if it's a code block of one line. Okay, the reason why it's because it can be confusing, and that kind of stuff. And so I normally see it this way. You might see some code online where there is no, if for one statement, as an example, there's no curly braces. That is bad practice. It's it can lead to error-prone code writing, which is bad, and we don't want to do that. It's a little longer, right? Because it adds curly braces to your code. right? But that's okay. I'd rather have it longer than more, kind of more readable than something that is difficult. Yeah, exactly, Justin. That is like bad. Okay. And what if I wanted to add something else? And some people, what they do is they indent their code to show that that one line of code belongs to the previous line, right? And the problem with it is it's okay. This is all part of learnings that we're talking about. I'm talking about code style and kind of our best practices. So that's why I'm sharing these things with you as well. So, and remember that anything we talk about in class, guys, safe environment, you guys can talk about anything. I'm not judging at all, by any means at all. I want you guys to learn. That's what it is. And my assumption is that you don't know if you're asking questions or whatever. I don't expect you to know anything beyond what I've shown you. Because I think when we talk to Rin and some other people here, I've been told that, some of the coding stuff that you've been shown is low in terms of depth. And so we'll add more depth as much as we can this semester. Let's continue. So we look at code like this, and then we try and decipher it. And I want you guys to start looking at code. And if you see code, you're like, okay, I understand what's happening here a little bit. So let's take a look. So here's a function called sequential search or sec search, right? It takes in 2 parameters. So the first parameter is an integer array, and the second parameter is an integer value. Okay, so 2 things. So the integer array is clearly the object that we're searching through, some kind of collection of objects. And the second object, the second parameter is the value we're looking for, okay? So one thing that you can see here when we're looking for integers is the system that C# is really good at comparing values. So comparing an integer to an integer, no problem. But what about when it comes to sorting and searching cards? Cards are a complex object, right? We just talked about this maybe a little bit last week, where I have the card that has a suit and it has a rank and it has some visual information and a bunch of other stuff. How do I compare cards? We could compare cards on value, but we got to set up this thing called a comparator first, because I can't really tell the system to do a sort of cards without some kind of value. So we're going to kind of come to that maybe at some point soon. All right, let's take a look. So here we're doing a for loop. We start at 0 because we're using 0-based counting as again for indices, indices in an array. We're looking to go from 0 to the array length minus 1, right? So kind of 1 less than the array length, and then we incrementing the index, okay, as we go. So this is how it works. We're saying that if the first element in the array, let's go for index 0, is equal to the value, then return true, right? And then we keep doing that. And if we run out of values to look for, we're looking for a value that does not exist in the list, then we're going to return false. Okay, that's how it works. So it's kind of a very simple way of doing things. And the downside to this is, again, if my array length is 5,000, 50,000, 200,000, 1 million, it's going to keep going until the entire thing is done. And it can take a very long time for us to get back a result if it's found or not found. And sometimes it can seem like it's just going on forever. And people, we don't like to wait more than a second, right? Imagine you're going in a website, you're doing a search, and it's just searching and searching and searching. You think it's broken, right? But it might just be searching a large list if it's a sequential search. If I'm going through an item, like a sequential item. A lot of times I look at this like a brute force search. I'm looking for every item in the list in a brute force way. Brute force is like, I'm just like a barbarian. I'm looking from one, house to the next for something that I'm looking for. Imagine I'm in a barbarian in a village. I don't know, something like that, or in a city. Then I'm breaking into each house because I'm looking for an item. I don't know. That's why I feel like that's what's happening in a brute force search with no mind. There's nothing intelligent about it. It's like literally going from one house to the next. And there's no way to do it because it's the way it is. Brute force searching and brute force kind of algorithms are dumb searches. They're dumb algorithms. They just kind of work eventually, but they're not very optimized. And what we want to do is make an optimized informed search. Okay, and that's going to be later on this semester. So the way this would work, of course, is I would use the search algorithm here. So again, I might have a series of numbers that I read from a file. That's what this little piece of code does. I search for an item in a file, maybe, for example, someplace like numbers.txt. Maybe numbers are in a random order from 1 to 100 or something like that. And then in this random file, I'm going to search for numbers that I load into an array. That's what I'm doing here. And I'm using the sequential search function to do that. Not very exciting. Okay, so what about, again, if I want to return the value. So the first version of the algorithm, it returns true if we found it. Yeah, it's there. That's all it says. But it's not really practical. Something like this is better, where I want to return the index of the in the array where we found the item, or return a -1, where -1 means there's no, we haven't found anything. Notice that we have to return a -1 because I can't return a false. Why can't I return a false here in this example? So there's two options: either return the index or false. Why can't I do that? I'm just talking about basic programming 101. Why can't I do this? And this is just reviewing functions. Justin says false is not an integer, and that's very true. But why? Why doesn't I can't do this in programming? You're right, but go further than that. Tell me more. And it's not a trick question. I want you just to explain more about why. I'm not sure if you're typing it, but yeah. Yeah, so it's true. But here's what I want you to think about. The function returns an integer. This is the integer return. This is the return type of the function. And there's no trick to this. It can only ever return one data type. That's what functions do when it comes to returning things, right? So that means that if I'm returning a value outside of this function, I can only return one type of object back out. Okay, the object could be a primitive type, like an integer, or it could be a complex type, like a struct, or an object like a card, like we've been working on. But you can only ever return one type. And false is a Boolean, and the index here is an integer, and that's two different types. And that's why notice that most algorithms return a -1 when the card or the object that you're looking for is not found. That's how it normally works. And it's because functions can only return a single type. All right. Now, there are some languages that can return multiple types. JavaScript is an example of that language, where it doesn't matter what you're returning, it'll return whatever you want it to return. That's a weird asymmetrical type of return type. It's really more flexible in many ways than this, but it's also error prone because you can get stuff back out of there into a value or a variable that you don't even know what that type is as you're looping, which is kind of weird and unpredictable. Right here, we have a predictable return type, an integer. Okay, that's why it's done this way in most coding languages. They're more strictly typed, like, for example, C++ or C#, or other languages like that, like Java. All right, one other thing we do a lot is searching for a specific type of value. I want to find the minimum value. I want to find the maximum value, right? And this is really important, minimum value and maximum values, because we use this for things like AI. I want to find the minimum, kind of distance, the minimum distance between A and B. What's that distance, right? And we can use minimum and maximums to do that. Min and max functions exist, and so do searching functions in C#. It's not like you have to write things manually. You just need to understand how they work and how you would write something like this manually yourself if you needed to. Because sometimes we need to make a manual search or write custom code to do searching with our own data types that we're writing. Example, our card class. So here's an example of finding the minimum value. The way we work is we assume that we assign the first value as the minimum. That's typically how we do it. And then we look through, again, sequentially through every item in the list as an example. And if we find another value that is a minimum value, then we return that item back out. Okay, that's the minimum value that we're returning. And that's what this is doing. This is returning the minimum value, whatever that is. It's not telling us where the minimum value is in the list, but rather returning the minimum value out. Okay, and it's just going through each item in the list and looping through each one of them, and then returning out the one that we find. Again, not a great usefulness, but and finding maximum is the exact same way. I just kind of set the maximum to the first value and then sequentially loop through each one and then compare each one with this one until we find the maximum value. All right. So again, a nice, more reasonable one would be like, yes, I found the minimum and here's where it is. Okay, that would be better if we could do that. Okay, so that is minimum and maximum, right? Which is something that we can do. That's very common. It's a common search technique. We want to look through and find those values. So one thing we can do to make it a little faster, the sequential search, is we want to make it self-organizing. So this is kind of interesting. Imagine if we're sorting a list of items and we have common items that we're searching for over and over again, right? We want to put those common values near the front, right? Because if we put the items that we're searching for near the front, most common values, right? Then what's going to happen is we're going to find those values much quicker, right? So if it's something more common, it's almost like a probability matrix, like I'm building up. It's almost like, let's suppose I have 100,000 numbers, but there's a certain grouping of numbers that I look for more often than others. I want those in an unsorted list like this to be at the front, right? Which is that way it can return it much faster. It can seem that the algorithm is more powerful and more organized. How do we do that? We're going to move the item that we search for, any item that we search for, at the front. So we're going to do some swapping, right? As we go. So as we search, we're moving those items to the front. And you're going to see that that has a way. If I search for that same item again, it's going to be at the front, right? So a little bit more optimized, but not much. And here's how it could work, right? So we have a sequential search again, and we're looking through each item in the list. But this time what we're going to do is we're going to swap. If I look at the index, here's my index that I'm looking for. And if that is equal to the value, let's suppose that, I don't know, somewhere in the array, I'm looking for that. I'm going to swap, kind of the object that I'm looking for with the object before it. I'm going to move it one place closer to the front. It's almost like it's going to take a higher priority, if you will, in the entire data set than where it was. So example was, let's suppose worst case scenario, I'm looking for an item and it's at the very back of the data set. Like let's say out of 100 items, it's like the 100th position. And if I look for it in the first time, and if I'm looking for that value, it's going to move to 99. And if I look for it again, it's going to move to 98. And if I look at it for it again, it's going to move to 97. And it's going to keep moving up and up. The more often I look for it, the more popular it's going to be, the higher priority, and the more efficiently I'm going to return that item in the list. Okay. So that's kind of a way of self-organizing code. It's nothing that you do, it's the code kind of optimizes itself as you go. Neat idea when it comes to coding, but really limited in terms of, especially with larger data sets, you have to have many thousands of searches or hundreds of searches for that to really bubble up to the top, especially in an unsorted list like this. Okay. We, of course, use the swapping algorithm. We've seen this swapping mechanism last week where we kind of take a temporary variable and we kind of assign it the value that we're looking at right now. And then we take that value that we're looking at, swap it out with something else. So we don't lose the value. And then we take the value that we've temporarily saved and, kind of put it into the second value. That's a way of swapping between two, right? So we have to have a temporary variable to do this, in place. Okay, this swapping algorithm is very common, and there's actually a name associated to it that if you look up is interesting, but this is the same way. It's like 3 lines of code, and we use a temporary variable to do that. All right, the problem, is we can, we're accessing stuff, and we're going to move things around quite a bit. There's ways of optimizing it even further, and here's a couple of ways we can achieve this goal. One way is to swap found items if they're located away from the beginning of the data set. So what happens if, like example, you find an item, it's already at the beginning. There's no place to put it. That's a problem, right? You can't swap it with an item that's before it because there's nothing before the data set beginning. That's a problem, a real problem, right? It'll error out. And the other one is swap a found item with the element that precedes it in the data set, which is what we showed there. So that's what happens. We just one before it, only if it's not the first item. If it's not the first item in the list. Okay. All right, so that's kind of the way we can do it. Let's move on to binary search now. So linear search or a sequential search, bad. Okay, bad because I'm searching for every single item. But let's think about a way of doing things in different order. And when we think binary, it's almost like there's two parts usually when it comes to binary. Binary code, binary numbers, 0 and 1, 2 parts, right? There's lots of examples of binary, in nature. All right. So, and here we're going to break the entire data set into 2 parts. That's where we are. And think about a guessing game. All right. And I kind of put the guessing game on the next page here, but I want a guessing game. And let's suppose, remember, a binary search only works if properly, if it's in sorted order. All right. It won't work at all. It'll fail if it's not in sorted order. Okay. And the reason for this is because we can assume that the lower values on the left and the higher values are on the right, like a priority or a sorted priority. Okay. So example, let's suppose I'm looking for a number like 7, right? And I'm playing a game with a friend, and I've got numbers from 1 to 9. Okay. So my friend has a number in their mind, 7. This is kind of a game we used to play as kids. With my kids, I used to play the game. I said, I have a number in my head. Okay, fine. And then it's a number from 1 to 10 or 1 to 9. Great. I tell them the range of numbers. And then what they say is, okay. And if I tell them 1 to 10, they might say something like 3, because kids, they'll, kind of call out a number. And then I'll say higher, right? And then so they'll say 4, higher, and they can keep going like that. And that's not very efficient. The right thing to do is, and smart things to do is, if I give you a range 1 to 9, you want to pick the midpoint, right? That's the first thing. You want to say 5, right? In this particular case. And then I'm going to say, if it's the number 7, I'm going to say higher. So now, if it's higher than 5 and it's as high as 10 or high as 9, then you're going to look for a number in between 5 and 9, which is actually going to land on my number 7, right? And so in 2 guesses, you can get the number, right? In this case, let's pick another number, another example. Again, I'm going through this, just please forgive me. I know that you guys get this, but I'm going through this. So this is how the binary search works. Okay. All right. So here we go. I'm going through a number from 1 to 9, and I say the number is 2 now, right? That's the number I'm thinking about. And you say, because you're optimized, you say 5, and I say lower. So now you look left. Okay. And then you would say 3, because that's the right thing to do. You would split that in half again. 3, and I would say lower. Now it's between 3 and 1. I'm going to say 2, and then you're going to say yes. So now look at that. I made 5, 3, and 2, and I get the guesses in. I did it in 3 steps. That's how binary search works. It actually breaks up the data set in half, divides it in half, and then looks either to the left of that number if it's lower, or to the right of that number if it's higher than the midpoint. Okay. And that's what it does. If it is the midpoint, that could be a guess too. It stops, right? That's also a possibility, right? So, but we normally wouldn't start at the beginning because you're going to have many more guesses. Like, if I start at like 1, then it's always higher than 1, and 9, it's always lower than 9. Doesn't give you any information. It's an uninformed guess if you're starting at those extremes, right? You never want to guess 1 or 9, because it most likely you'll probably guess more than once, to get 1 or 9. It's usually not that, especially in a larger data set. For example, I have 1 million numbers, and I have a number in my head, right? It's going to take many more guesses for 1 million numbers. So, you're going to start at 500,000, and then now you're going to know, is it higher or lower? Right there, I've canceled out half of the data set. It's gone. I don't have to think about it anymore. I've eliminated it, right? And then I can go through, keep on cutting it in half and cutting it in half until I get zero in on that number. That is a good example. Binary search is more efficient than sequential search. And see why? Because I'm cutting things in half every single time, right? And that's the good thing about it, right? But a binary search requires the entire data set to be in sorted order, which means the dependency means that I have to go through a sorting step first, to make it more efficient. Okay, so that's required. So first sort and then binary search. That is the way to go. Otherwise, this won't work. Can't do higher and lower because you don't know if it's higher or lower. Okay, so this is kind of the way this works. So this is the 1 to 100 game that I just talked about. I just used 1 to 9. And then you want to find that midpoint and then kind of go within that midpoint over and over again. And we can look at a piece of code like that with a while loop. Here's a while loop, right? That kind of runs through. And what we do here with the while loop, I'm just going to zero in here so we can see it a little bit better. With the while loop, you have an upper bound and a lower bound and a middle. The upper bound would be the higher end of the number. So if I said from 1 to 10, 10 would be the upper bound, 1 would be the lower bound. The midpoint would be whatever the upper bound plus the lower bound is divided by 2, right? And rounded to the nearest integer value in this particular case. Okay, that's what you want to do. And then once we have that midpoint, what you want to do is you want to sit there and say, okay, so let's take a look at the midpoint. Is it the value that I'm looking for? If it is, stop, because that is a possibility, right? And if it's not, that's my first guess. Is it the midpoint? No. Well, then if it's not the midpoint, keep looping, right? Then I want to say that the value, if the value is less than the midpoint, right, then the upper bound is now the midpoint minus 1. So now I've kind of looked at the midpoint, whatever that number is, minus 1, and that is our value because it's not the midpoint, right? This is actually better than what I did earlier when I was guessing, right? When I was going here, it was better than this. I didn't say, well, now it's 1 to 5. No. We know it's not 5 because I guessed 5, right? So it's between 1 and 4. What's the midpoint between 1 and 4? 2, right? Is it lower than 2? No, then it's 3. It's like just simple, like that simple. That's how it works. So that's how the general algorithm works, where we look at the midpoint and then we look at the upper bound is now mid minus 1, right, as an example, but the lower bound is still the same. That's only if the value is less than the midpoint. If the value is greater than the midpoint, then now the lower bound is mid plus 1, the middle point plus 1, because it can't be the middle point. We already asked you for the middle point, and now it's between that one and the end. And now we're going to loop again. We'll go back and loop again, and we say, okay, if the lower bound, while the lower bound is less than or equal to the upper bound, right? This is where we stop, where the lower bound is less than or equal to the upper bound. Okay. But when the lower bound is greater than the upper bound, right, somehow we're going to stop. Okay. And here's something. Notice that it's going to keep returning until the middle value is true. So this is kind of a weird loop when you look at this thing, right? There's a lot of other ways to do this, right? Where you can say that, it's either going to return the midpoint. That's the base case. This is the one you want to return. You always want to find the middle, whatever that is. And the reason why is because if you think about what that midpoint is, the midpoint you're going to calculate is the upper bound plus the lower bound divided by 2. So let's suppose, again, I look at those two numbers, right? Then that guess is going to always be the middle. I'm always guessing the middle. That's my guess. And I'm going to guess it eventually, right? I'm going to return. When I return, I break out of the loop. That's what I'm doing. I'm kind of getting out of here. I actually stop the binary search and I return a value. So this is kind of, I want to say, a destructive return. It's almost like I'm saying, cancel the loop, see you later. I'm leaving the function and I'm giving you the value, right? It's kind of like doing a break. I'm breaking the loop and I'm also leaving at the same time, right? So that's kind of it. It's almost like I can almost physically say that the value that I'm looking for, the only way this would be, what was this while loop would stop is if the lower bound is greater than the upper bound somehow. And if you look at these values, it's going to get you there eventually. If you break out of this loop and you're still inside this function, that's what this thing does. It's going to return a -1, which means the value isn't found. That's only if you're able to actually survive going through the loop the entire way, okay? So it's a weird way of looking at it, and you may write this loop, you may have written this, if I was going to ask you for an algorithm, you might write this differently, because you might look at it and go, I wouldn't write lower bound is less than or equal to the upper bound. Maybe I would write something like, while value not found, right? Maybe I can have a Boolean that says value found is equal to false, and then when the value is found is equal to true, then I break out of the loop. That's a more elegant way of breaking out. Okay, and I break out of the loop and then I return the value, right? This way is kind of rough. As soon as I find the value, I break out of the loop and I return it out of the function right away. And so that's kind of how it works. Okay. All right, let's continue with this this kind of thing. So so this is definitely one way of doing the binary search, but I want to talk about another thing, which is recursion. Okay. So recursion is something that you're going to see over and over again. And again, I'm going to, I kind of touched upon it last week, but I'm going to assume again that you don't know what I'm talking about when it comes to recursion. So please forgive me if you know. Okay. So here's, how it works when it comes to, here's what it comes to, this thing, right? So a recursive function is a function that calls itself. Right there, that's weird. How does a function call itself? I'm making the function, I'm writing the function, and then inside the body of the function calls itself. How does it work, right? Well, it creates copies of itself. That's what it does. So it's almost like wherever I get to that part of the function, I take that part of the function, I make a copy of itself and throw it onto the stack. And the stack, like I mentioned before, is kind of a location in memory. And what it does is it keeps track of the program flow, right? So if I kind of look at the program from the top of the program to the bottom of the program, I want to go sequentially one line at a time until I get to the bottom of the program, whatever that program is, right? And same thing with the function. I go from the top of the function and I keep going through that little code block until I get to the end of the function. When it's done, I return back to where this function was called, right? So I have a place where this function was called in the first place. I'm going to return some kind of value out to that location. All right, that's what I'm going to be doing. I'm going to return myself. The program flow is going to return back to that location. That's what's going to happen. But what about within the function? I'm calling that function itself. What it's going to do is going to create a copy of the function, put it on the stack, right? I'm going to kind of say, okay, well, here's a copy of this function. It's another function. But this function is going to return back to the place in its own function that it was called. And that's where people lose it. They're like, wait, what? That's right. And we're going to talk about this in a second. So it has iteration, it has advantages over iteration techniques. Why? Whenever I break a problem into smaller parts, it's almost like I have a task and I have several subtasks I want to do. Example would be, we're going to look at this later on in the course. I have a tree structure. I have a root and I have two children in the tree, a binary search that I'm doing with the tree, right? I have the left subtree and the right subtree. And I'm going to perform the same operation on the left side as I do on the right side. That means I could do the same operation on both sides, almost like I do the function over here, this magic, then I can go over here and do the same magic over on this side, right? Well, what if that is a good case for recursion? Because what it's going to do is going to say, okay, finish up all this side, go to do all the left sides first, come back, return the data from the left side, and now do the right side. Come back, and then keep going and finish off the tree. And it'll be done. It'll be looping through the entire or traversing the entire data set, but it'll loop through in almost like a weird way, right? That you haven't seen before. It's natural to write it this way, almost like writing a little bit of pseudocode. Pseudocode again is just us talking about how the thing should work. So let's go back before I go into this and let's think about this pseudocode. So, and how I would talk about this thing for a second, and then we're going to move away from this topic and actually do some code. But think about this. So when I'm talking about this number game that we're playing, I want to say, pick a number, any number from 1 to 9, okay? And you pick 5, right? Because that is the first part of the iteration. So divide the range in half, right? And then is that the number? Yes, then that's the number 5. If it's not the number, then what I want you to do is divide the range in half again. if it's on the left or on the right. Choose which way to go, on the left or on the right, and divide that range in half. Is that the number? No. Okay, choose if it's on the left or on the right. Divide that range in half again. See that subtask? Dividing the range in half is the subtask, right? And I'm trying to find that middle thing over and over again. I'm looking for the middle number over and over again. Is it that one? Is it this one? Is it this one? I keep on dividing it in half, right? And as I keep dividing it in half, that is the subtask that I'm doing over and over again, right? That can be turned into a recursive algorithm. So again, there's recursive and there's iterative. Recursive is exactly what I'm saying. Take a subtask and then use that as part of the recursive body of the function. Iterative, I'm going to loop. And anything you can do recursively, you can do iteratively, which means I can replace a recursive function in code with a while loop a lot of times, or a for loop. Okay. Let's talk about advantage and disadvantage of this technique. So here's an example. So properties of recursion, performing the same operation multiple times with different inputs. Okay. In every step, we try smaller inputs to make the problem smaller. We're trying to subdivide, right? And we have something called a base condition or something called a base case. Now, this is where it's going to stop us, almost like a sentinel variable or something that we're using that's going to be a condition to stop us, to break us out of this crazy loop that we're in. Otherwise, we're going to keep on looping forever, okay? And this is something that we can do. So here's the comparison between the two. So again, recursion terminates when the base case becomes true. Iteration terminates when the condition becomes false. That's the opposite, right? So this is where your thinking is kind of, it's hard to think this way, because for loop for 0 to I plus plus until this condition becomes false, right? Kind of thing, right? That's how it works. And then recursion implemented with functions, iteration implemented with loops. That's the difference between the two, right? Every recursive call allocates more stack memory. Every iteration does not require any more memory. That's kind of a good thing. Smaller code size or larger code size, less performance. Recursion is less performance. That's one thing you're going to note as well, right? Why? Because I'm allocating memory. Every time I allocate memory, it's an extra step. It's overhead, right? And if I have the overhead of allocating memory, it's going to be absolutely less performant, no matter what you do, right? And sometimes even less performant to the point where it's really slow. So recursive programming, generally bad when it comes to performance, right? And we're talking about performant algorithms here, right? Iteration, more performant. However, we'll talk about the reasons why you'd want to use it. Will cause a stack overflow on the left. That's recursive if it's not written correctly. So stack overflow, remember we talked about this last week. That's where the name comes from, because I keep on allocating or making copies of itself onto the stack. And now I'm going to do this other thing, and then make another copy on the stack, and I'm going to do this other thing. And if it's never going to finish, or if you just run out of memory because you're going to go through so many iterations deep, that's another option, where I don't know, I have a million iterations to go through, right? And the stack only has so much memory, and then you've run out of memory in the stack, it's going to stack overflow and you're done. All right. And the other way, it's going to cause something called an endless loop. If you don't write it properly, or if it's a lot of iterations, like millions of iterations, then the loop will keep going forever. Okay. And so both have advantages and disadvantages. Let's talk about when to use recursion. Here's case number one. So, when we're looking at a piece of code or something we want to write, and it's easier for us to write it in a recursive fashion because we want to get it going than to write an iterative solution, to write a solution with loops. Okay, it's just easier. When I look at it, I'm like, do it here and then do it here. The same task that I want to do over and over again, the same subtask in different parts. I want to do it on the left subtree or the right subtree or the middle tree, whatever. That's when we want to do it and exploit some kind of structural aspect of the problem, all right, that the iterative approach can't do, all right, as easily. And that means like things like I'm in a tree structure, like some kind of structure that I'm doing. Case two, we can be reasonably assured that the depth of the recursion will not cause a stack overflow, which means we're not going to go very, very deep. In other words, I'm not going to keep putting things on the stack forever. Like it's going to be something that is manageable. A good example of that is some kind of sandbox if I'm going to look at, let's say I'm searching for the shortest path from A to B. I have my player and my enemy, and I want to go from A to B, somewhere where the, kind of find the shortest path to my enemy, right? And the way to do that is, if it's not going to cause stack overflow, if there's not unlimited nodes, like millions of nodes for me to travel through, okay? And if there's millions of nodes, what I want to do is I want to break that problem down into smaller pieces, right? Which is something we'll talk about later on this semester, because that doesn't make sense. Why would I try and plot a path from A to Z right away? Maybe I want to plot a path from, kind of a midpoint, a checkpoint, from A to B, and then from B to C, and from C to D, because I want to break up the game world into smaller chunks until I find the last position. That might be something you can use recursion for. But remember, recursion is slower. It's more memory. It's a memory hog, and it takes up, it's a little bit more overhead, right? And that's a negative thing. But it solves problems. Sometimes too complex. If it's way too complex for you to solve iteratively, then this is just a solution, an option to to solve the problem, which is something we want to do. May not be the best solution, but it might be the easiest solution to write. Okay. Let's think about a recursive binary search now. So now that we've talked about recursion a little bit, we know that the recursive binary search is going to be a function that calls itself. And let's think about how this works. Okay. So here's a recursive binary search. So again, here is the base case. Take a look at this base case. If lower is greater than upper, then return -1. Let's take a look back at that previous set of code, right? So I said something like, if lower is less than or equal to upper, it's kind of the opposite here, right? I've kind of gone into opposite world where lower is greater than upper. It's kind of the same thing that I'm saying, right? But in a different way, right? So that's what I want to say. And I want to say that, kind of right here. So if lower is greater than upper, then return a -1. Else, the midpoint, make a midpoint, where the midpoint is you take the upper value and the lower value divided by 2. Same thing that we did last time, okay? So before, we're looking for that mid value, and that was the thing that we broke out of, right? Okay, so now we're going to say this. If my value, whatever the value is less than the midpoint, then do a recursive binary search again by taking the lower value, right? Whatever that is, as the lower value. And the upper value now is going to be at the midpoint -1. And now what's going to happen is, just to draw this out, this right here, it's going to stop operation of this function, and it's going to kick me out, just to show you how this is going to work. This is really interesting, right? That's why I'm going through it with you, so you understand how this works. It's going to kick me out at this point, right? This is where the binary search is going to start, it's going to make a copy at this point, right, of this whole entire thing. And now let's think about this. Now it's going to do the exact same thing with a new set of parameters. Okay, so the new set of parameters are, the lower value is the original lower value, a copy of the original lower value, and the upper value is a copy of the midpoint that we just made, right, -1. And then use that as the upper value. So now the lower value is the lower value. When I come back into this part right here, I'm going to go over here and just kind of kick into this part over here. This is the looping part. And then now the upper value is the midpoint -1. Okay, let's go through it. Is my lower value greater than the upper value? No. Good. Then my integer, make another midpoint, right? So another version of the midpoint in this scope. It's another function scope that's not the original midpoint, just another thing that's called mid, because remember, each function has its own scope where the variables live and die, right? And this is just another variable called mid in another copy of the function, almost like a parallel universe in some ways, right? No problem, Mark. So that's kind of how it will work, right? And then what happens is, okay, well, we make another midpoint, and we take the midpoint upper plus lower, and let's suppose we know that before when we left here that the value was less than the midpoint, and let's suppose that we have that number value from 1 to 9, and my value is 2. So I've said, well, 1 to 9, the midpoint is 4 as an example, and the midpoint from 1 to 4 as an example. Now we're going to go 1 to 3. The value is 2. Is the value 2? Right? Well, this is what we're going to say. If my value is less than the midpoint, no, This is the second value. If the value is equal to the midpoint, yes, return the midpoint back out. So this returns the function back out to the calling function, which kind of, I'm going to say this like this. It comes back where we left. It comes back to this point right here. All right. So now we've returned the value up here, return back out here, return mid, right? So that is the value that this returns, mid, right? And then what happens is, because we've done this, right? Then mid is the one that it wants to return. Whatever that mid value was, we returned it back out to this. Now, here's something that's really weird in this case, right? And notice it says there's really no return value. It kind of finishes this if statement and goes to the next one and the next one. And then what happens is it leaves this if statement altogether. So this is kind of a weird thing, the way this works. We haven't returned anything, right? But we're using the word return. Okay, so I want to just mention this for you guys so you understand what's happening. So we're using the word return. And this return, right, because this one found that the mid value was the one that the mid between the lower and the mid minus one, that's what it would have been, right? That was the number, let's suppose, right? And now we've come to this point in the new function, new copy of the function, and this is the case. Value is equal to the midpoint, and what I want to return is the midpoint. When I call return, right, it returns to this point, but we've called a return, right? And then you would think that you're going to go through this loop, and then you're going to come to the point at the end of this function. It's going to be here, right? There is no return at the bottom of this function, which is, it should return something at the bottom. There's no return type. And this function, every function should return something. This is supposed to return an integer. Here, we didn't return anything. And here, we didn't return anything. The only time we return something is when we hit here, when the value is equal to mid. But because we use the return keyword, return actually returns back out, and it returns back out this function. And it gives us our value. This is not always how it works. Okay, and this is kind of a really weirdly written function, the way it was written. I didn't write this. This is kind of something that came from the book, but I just wanted to talk about this. All right, let's suppose also that maybe it's not the midpoint, right? It's not the midpoint at all, but maybe it's kind of something like, well, between those two values, we searched for the midpoint again. We thought it was 2, but actually it's 3. The number is supposed to be 3. Okay, let's suppose that's it. So then we're going to do this binary search between the value, as an example, that we want to put in there, 3, and the new value that we're going to put in there that we're searching for, because we notice that the value keeps on iterating through the entire thing. We're kind of searching for whatever the value is in the entire kind of in the entire thing. And we're saying that we're going to use the value that we've passed through the entire way. So let me talk about the recursive binary search and show you how this is used. Okay, as an example, one more time, and then without confusing the crap out of you, because I know this is a confusing thing, right? That's why I'm bringing it up. Let's put some values in here that we want to talk about. So let's do a couple things. Let's clear up this little map. And let's make the number. So again, if we assume the numbers are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's make it from 1 to 10. Okay, so let's do that first as an exercise. So here it is. So here's 1 to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We know that they're in sorted order because we're doing a binary search. We know this. So if I say my number is between 1 and 10, and you're going to guess the midpoint, you take 1 plus 10, the lower bound plus the upper bound, 1 plus 10, which is 11, right? Divided by 2, which is 5.5, and then round down to the nearest integer, which is 5. So that's your midpoint. Okay, just to show you this, right? So now that we've rounded down, kind of to the midpoint, right? So that's the first thing. So this is the midpoint. And what we want to do with the midpoint is go, okay, cool. So if this is the midpoint, right? And this is the number. Is this the number? Right? If lower, now look, think about this. This is the number that I'm searching for. My value, my lower and upper bounds, and I'm going to search for a value that's in the middle. Right? Before I come in here, I'm searching for that middle value. All right. So I'm saying 5. 5 is the value. So we're going to say that the value starting off, when we first start off this thing, the value is equal to 5. Okay, starting off. Think about this for a second. That's the value, 5. So value is 5. The lower bounds, right, is 1. Okay. Just to show you, right? And the upper bounds, right, is equal to 10. Right? If the value is 5, if that's the value, right, then it goes like this. Is lower greater than upper? Lower is 1, upper is 10. No, right? Else, mid, let's make mid, and mid is going to be equal to, right? Mid is going to be equal to the upper plus the lower, so 10 plus 1 divided by 2, which is 5.5, which is 5. Okay, so mid is equal to 5. Here's the way it works. And then you're going to say, okay, cool. If value is less than mid, value, right, is less than mid. No, that fails. If value is equal to mid, then return mid. So now it's going to return 5. That's what it's going to do. The value is 5. That's where it's going to be, the integer where we found it in the list. That's going to return where we're finding it, 5. And we're done, right? Because 5 was the number. That's the number that we're looking for, and 5 was our guess. Okay, cool. But let's do it another way. Let's undo these changes, and let's go with, we say the value. Let's say the value is 8. Right, that's the number that we want to find. Okay, the value is 8, and then this is how this binary search works. And then we say that the lower is equal to 1, and the upper is equal to 10, just like before, right? And then we say that the midpoint is equal to 5. We saw that. So now we go through this again. We say, is the value less than the midpoint? Is the value less than the midpoint? No. So this is no good. Is the value equal to the midpoint? No. Is the value, greater than the midpoint? Then that would be yes, because this is the last point that we're going to go to. So now we're going to recursively search the new value, 8, and the midpoint is going to be the lower, and the upper bounds is going to be the upper. So now in the new version of our code, lower is going to be, let's do this again, lower in the copy. So this is our copy, right? And we're going to say lower is equal to 5, right? Plus 1, 6. So we know it's not the midpoint. And the upper is going to be 10. Okay, that's the first thing. The value is still going to be 8. Value is still going to be 8, right? That's the value. And now the midpoint is 6 plus 10, which is 16 divided by 2 is 8. That's how it goes. Okay, so it's 8. And now we go, in this thing we say, is the value less than the midpoint? No. Is the value equal to the midpoint? Yes, it's true. Return mid. So I'm going to say that the return value is mid. So return mid, right? Which is return, the value would be whatever the value is, the midpoint, which is 8. Okay. And then once we return 8, this return goes back to where we returned over here, right? And when we say return, it returns out of this entire function and stops the recursive call. That's how it works. Okay. Right? And you might think that this is weird, and it doesn't work like this in every language. Sometimes you have to have an explicit extra return statement that says, okay, when this is found, value is found, return whatever you found. You have to have a return statement that goes back and back and back and returns back to where the calling function came from. Okay. Hey, Scott, how you doing? Glad you joined. All right, so that is kind of a little bit about recursion, and like we said before, it's not always something that you want to do, right? But sometimes it might be easier for you to write. I personally think that it really depends. if, sometimes recursion itself is a difficult thing to wrap your mind around, right? Because when you're looking at a function, it's just easier to write it iteratively, right? But there's times where both things are really bad, okay? And there are some cases where recursion is like, there's almost like famous cases for recursion, okay? And one of those cases is called the Tower of Hanoi. Okay, let me just bring this up for you guys. So if you look up the Tower of Hanoi, so the Tower of Hanoi game is kind of a game which is mathematic in nature. You have a kind of a tower, a stack of these rings, if you will, and your goal is to move the stack of rings, right, all of them in the same order to the other stack, to the third stack, right? And you want to do that one ring at a time. Okay. So if you think about this, is the iteration. You take the top stack and you put it at the bottom, and you can see that eventually what's going to happen is what we want to do is we want to take that stack and you're going to move it back and forth until you have everything. You're making like almost like substacks until you move everything to the right hand side. So this is kind of a way of doing that. And if you think about this idea, the Tower of Hanoi, right? It's a recursive problem because I have a subtask that I'm doing over and over again. Okay, that's what I'm doing here. So Tower of Hanoi. Okay, the other one is Fibonacci. If I want to find the Fibonacci sequence, right? The Fibonacci sequence is a number that goes, 1, and then what you want to do is starts at 1, 1, and then you, in order for you to get the next number in the sequence, you got to take the last two numbers and add them together. Okay, so that's how it works. A sequence. That's another great, kind of figuring out a sequence of numbers. So so if I say 1 + 1 is 2, then you take whatever that last thing equated to, and you're going to say, well, the next number is you want to take the last number, the last two numbers, and make the next one 3. 1 + 2 is 3. 2 + 3 is 5. 3 + 5 is 8. 5 + 8 is 13. But the question would be something like, give me the 23rd Fibonacci, the number in the Fibonacci sequence. How do I get that? I need to do a recursive list of numbers. You can do it with a while loop as well, right? But you want to find the next number, the next number, the next number based on, kind of the number in the sequence. Fibonacci is found in nature, and you can see that it's called Fibonacci spirals, as the number keeps on growing, in a very, it's not even, it's kind of an exponential growth, if you think about it, and how it works in a lot of different things that you might see in nature, especially in plant life and other organic things. So an organic sequence, which is something that we want to use. One of my friends is a good example, is making a game right now, and a lot of his leveling up is happening in kind of a Fibonacci sequence, because it kind of gives you a natural progression that makes it very hard to get to a higher level. And as you can see that, like, look at the numbers in the sequence here, in this little thing here, you can see that this is the first level or the second level, right? As an example, first level is 1, the second level is 2, right? And the third level is 3. So this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. By the time you get to level 13, the cost for getting there is 377 points compared to a very linear cost, right? Again, games don't necessarily like that anymore. You want almost like a linear progression for experience in games. But, this is kind of a way of thinking about that too, the Fibonacci sequence, right? Which is kind of neat. So that's another thing to do. Factorials as another thing to use for numbers, for recursive numbers. So factorials, the factorial sequence, right? Factorials are interesting because, factorial is the number, multiplied by the previous number, as an example. And so the factorial might work like this. So factorial of 0 is 1, factorial of 1 is 1, factorial of 2 is 2 times 1, factorial of 3 is 3 times 2 times 1, and so on until you get like a very crazy number in like, factorial 10, or 10 factorial is what they call this. 10 factorial is like, this big number. And it gets pretty big, pretty goddamn fast, right? That's how factorials work. But you need to calculate this number. So the challenges with math and with programming is two things: how to make this number work. You can see that there is an iterative nature to this sequence, right? And the next thing is, as these numbers keep getting bigger and bigger, right? How do you represent these numbers in code? like on the computer, because they're going to come to the point where it's going to be very big, very, very fast, right? So that's the kind of the challenges that you have. And you can see that there's some bigger, kind of groupings of sequences of numbers that are very, very big, very, very fast, okay? All right, so that is some examples of where, you would do it and why you would do it. A lot of times, when you're programming something like this, where n times n minus 1 times n minus 2 times n minus 3 times whatever, those things are ways of doing it. The other one you might want to use when it comes to AI is, kind of sorting, searching, a searching algorithm. So if I do searching algorithm, and if I go some kind of recursive searching algorithm in AI, if you look that up, right, you're going to see that it starts looking at trees again, or some kind of graph like this, right? Where I kind of look at, especially with a binary example, here's a binary tree example, where I have the left subtree and the right subtree. Okay, notice the left subtree is symmetrical with the right subtree. Smaller tasks, I'm breaking it down into subtasks, right? It's almost like exactly what I just said. If you think about this, I have, if I think about this, I have, this is one subtree right here, and we can treat this as a tree, right? Where you have the root of the tree right here, right? And so too, this was the root of the tree, and this was the big tree itself, right? This is the big tree, but you have a subset, which is this left subtree. Okay, and then from this one, you have this left subtree. You can see that this is a recursive thing where things get smaller and smaller, just like that mirror that you're looking into, and then here you have the root, and then you have this left subtree, but seeing that this left subtree is actually a leaf, and this is the base case. Now I resolve this one, right? And I come back to this one and do the right subtree. Good, I've resolved this one, I've resolved this one. Whatever the thing I'm resolving, I'm recursively traversing the tree. And then I come back out to this part as an example. And now I look at the right subtree. The right subtree, I look at here, and then I do the left subtree. So I do the left one first, kind of resolve this one, then do the right subtree, which resolves this one. And then finally I come back here and this is resolved, right? And then I come back up here and I go to the right subtree. Here's the right subtree. And now the right subtree, well, I look at the left subtree first, because that's the thing that I've been doing. And I cut this down into this part right here. And you can see how that repeats. The steps repeat every single time. It's a repeating number of steps, a looping structure that is cutting a problem down smaller and smaller pieces. Okay, that is tree traversals. And we do this when? Decision making. If I want to use a decision-making algorithm where the top says, do I have line of sight? No, go to the left. Okay, can I sense the player? No. Okay, patrol, right? That might be this leaf right here, patrol. Okay, do I have line of sight? No. Do I sense the player? Yes. Okay, then move to line of sight. You want to get closer to the player, all right? Do I have line of sight? Yes. Am I close enough to attack the player? No. Move closer, right? Make sense? And so you can see that the subtree, this whole tree algorithm can be used for AI, which is really beautiful as well. All right. We're going to get back into this later on, but I wanted to kind of go through this in an exhaustive way because search is a fundamental a thing to do, and so is sorting. We did sorting last week, searching this week. You should have an idea of what both things do and the challenges about how to make things go. Questions around searching or sorting? Because we did sorting last week and searching this week. How about searching? All right, let's stop this recording now. This is the lecture recording. And when we come back, we'll start getting back into some stuff that I want to help you with your assignment 1, which is what I want to do as much as I can. So let's stop this now. We'll take a short break. We're sitting at 9:48. Let's take 10. We're going to come back at 10, right? And then, at 10 o'clock, we'll start doing the in-class exercise, okay? Best brute force search, sure. We're a sorting algorithm. Take a list and make a list of lists with n values. Sure, n factorial. It contains all possible permutations of list set. Increment through R and go to the, oh God, That is definitely a brute first search. Interesting. Thank you for that. All right, we'll come back in like 10 minutes, guys. Thank you so much. All right.